One thing that comes up pretty often in Newton's second law type problems is objects that are rolling or sliding along a surface. And, so let's say that there's this inclined surface and you'd have an object that would be represented as a box or as like a cart. And in problems like this, this cart, and it's true with sliding problems too, this cart can't sink into the surface and it can't jump off the surface. So we know a lot about the motion that's happening. The velocities and accelerations are only going to happen parallel to the surface that it's rolling or sliding along. And in problems like this, we're always going to choose a coordinate system. For now, up until now, we've always been using just sort of the standard orientation of coordinate system, but now we're going to start using a coordinate system where the y-axis points directly out of the surface and the x-axis does what it needs to for this to be a valid coordinate system. So the x-axis is always parallel to the surface. So the y-axis is directly perpendicular out of the surface. And then that means that the x-axis is, let's say, along the surface. Okay, well, there's no reason you have to do it this way. You could keep the standard coordinate system and do all the calculations using a standard coordinate system, but there are benefits to doing this. So I want to point out what the benefits are for using this sort of funky coordinate system. So on this side, I'm going to list all the benefits. And then on this side, I'm going to list a single drawback. Okay, so using a coordinate system like this with Newton's second law, the first benefit is the acceleration is always in the x direction only because it can only slide along the surface. That a could be negative or positive, but we'll always represent it just as a0 and then we'll calculate the sign of that a. There's also always a pushing force, a normal force, a pushing force from the surface that's always going to be 0n. And in this case, that n always has to be positive. Let me, I guess, write this as, this can be plus or minus. This one has to be positive. Excuse me. And then there's a third benefit, and that's in problems where there's friction. Now notice in the example that I drew up here, there's no friction because it's wheels, but if it's sliding, a lot of times there will be friction. And friction is always going to be in the positive or negative x direction. We'll know which direction that is, so I'm going to put that plus or minus actually in here because we'll do that ourselves. We won't calculate that. And so the x component is plus or minus coefficient of friction times the normal, and then 0 for the y component. Okay, so instead of these things being complicated, the acceleration, the normal force, and the friction force, instead of them having x and y components that you have to use sine and cosine for, they all have this really simple form. That's the benefit. There's one drawback. One thing that gets more complicated using this reoriented coordinate system, and that's the weight force. The weight force up until now has always just been in the negative y direction. But now it's not going to just be in the y direction. We're going to have to write it as mg, and remember that g is positive 9.81, so this is just a magnitude of the weight force. And then we're going to have to multiply that by a cosine of an angle and a sine of an angle. Okay, so now instead of just sort of instantly writing down the components of the weight force, we're going to have to calculate that. And one thing that I want you to be aware of is that, I mean, all we're doing in calculating using cosine and sine is figuring out how that, what the angle theta is that you have to go counterclockwise from the positive x-axis to the weight force vector. Okay, but there's one thing that is always going to be the case, and that is that theta is going to vary from 270 degrees by the same angle that the surface makes with the horizontal. Okay, so if the surface is horizontal, then it reduces just to the normal coordinate system. Your y-axis points straight up. The angle that the surface makes with the horizontal is 0, and that means that the weight force is exactly 270 degrees, and it's exactly the way that we're used to doing it. But if you have like a 20-degree angle of the surface with the horizontal, then that weight force is going to either use a theta of 250 or 290. It's going to be 20 degrees off from the 270. So that'll make it easier to do these. So I'm going to do one example first without friction, and then I'll talk about a couple of friction problems, or I guess I have one friction problem to do after that. Okay, so the first example. So let's say that we have a ramp like this. All this noise you hear is our little puppy messing around. Would it be nice if he was doing it in the other room? Okay, yes, it would be. Okay, so you have a cart that's rolling on this surface. Okay, and let's say that this has a mass of 10 kilograms. That angle is 20 degrees, and we want to calculate the acceleration vector of this cart. By the way, so we're going to calculate the acceleration vector. You'd see that no matter what mass you used, if you tried 20 kilograms, 5,000 kilograms, half a kilogram, all the accelerations would be the same. It doesn't matter, but I'm just putting that in there so we have a number to put in. Okay, so the first thing we have to recognize is that this is a rolling or sliding problem. And so we're going to put the y-axis straight out of the surface and the x-axis along the surface. And then I'll go to a free body diagram. Okay, so what do we have? Well, we still have the weight force. It's just not parallel to the coordinate system anymore. And the magnitude of the weight force is still 10 kilograms times 9.81. So that's 98.1 newtons. And then there's a pushing contact from the ground that is perpendicular to the surface. So these two vectors are not parallel on this because of this incline. I'll call that N, the normal force. And there's no more forces acting on the boundary, so we know we're done. And now we'll go to Newton's second law. So Newton's second law, if we put these forces in, that normal force is in the positive y direction because of our rotated coordinate system. That weight force, now if you think of our coordinate system at an angle, let me get this a little more accurate. Okay, so there's our coordinate system. And the weight force still goes straight down, so that looks like this. Okay, so what's the angle? Well, we know it's going to vary from 270 degrees by 20, one direction or the other. And you can see here that it's going to be 20 degrees past the 270. You get to the 270 and then have to go 20 degrees farther. So that's 290 degrees. This theta is 290. Or you can also do it as minus 70. It gives you the same answer. So this is going to be 98.1 times the cosine of 290, 98.1 times the sine of 290, and all that, the forces added together are equal to the mass times the acceleration, and like I said, we'll write the acceleration as a0. Since all we're trying to get is the acceleration vector, all we need is that a. So I'm going to use the x component of this equation. 98.1 times cosine of 290 is 33.55 plus 0 is equal to 10a. And so a is equal to 3.355 or around to 3.6 meters per second squared. So now to write the acceleration vector, take this value for a that we just got and plug it into our acceleration vector that we used in Newton's second law. And you get that the acceleration is 3.360 in the coordinate system we were using for this problem. So that's that sort of rotated one. Or another way to think of that is a magnitude of 3.36 in the direction of the positive x-axis, so down the ramp. Okay, so that's an example of a rolling problem. There's kind of one more thing you have to do when you're dealing with sliding problems that involve friction. If you have a sliding problem with no friction, it works just like this. But so let's talk about sliding problems with kinetic friction. These are the only kinds of problems where in order to do the problem, you have to know which way the object is sliding at the instant you're looking at. You need to know the direction the object is sliding. In other words, the direction of the velocity vector. And the reason you have to know that is because the friction force is always going to be opposite of the velocity vector. So, you know, friction is just always trying to slow things down. So if the object is moving to the left, the friction is to the right. Let's see. Okay, so You need to know the direction the object is sliding at the given instant. The friction force is always opposite that direction. And the magnitude is always the coefficient of kinetic friction. That tells you how much friction there is naturally between these two materials that are sliding against each other, times the normal force that's pushing them together. So that friction force is going to get bigger the harder two objects are pushed together. And when you're doing these problems, there's always going to be, you're always going to approach it the same way. First, you're going to use the y component of Newton's second law to find the normal force. Then you're going to plug that normal force value into the x equation to solve for the acceleration. Okay, so we're going to set it up sort of the same way as we did for that rolling problem. The difference is in the rolling problem, we didn't need the y equation for anything. In friction problems, we're always going to use the y equation first and then plug what we get from the y equation into the x equation. Okay, so let's say that this time we have a ramp facing this way. I'll say this angle is 25 degrees. And we'll say at this instant that we're analyzing, the box is moving up the ramp. And it's important to recognize that this is possible, even though you might say like, well, what's making it go up the ramp? There aren't any forces acting on it, pushing it up the ramp. Well, we don't know what happened to this box before this instant we're looking at. Someone could have given it a really hard shove, and then we're analyzing it half a second after they gave it that big shove, and it's still sliding from those forces that happened before the instant we're looking at. And so even though there are no forces in our picture that would make it slide up the ramp, it still is perfectly possible for it to be sliding up the ramp at the instant we're looking at. We're going to say that the coefficient of kinetic friction between the surface and the box, sometimes I write it just as this mu, sometimes I write it as mu sub k to make it clear this is kinetic friction, not static friction. We're going to say that's 0.0, not 0.01, 0.1, so not a very big, not a lot of friction between these surfaces. And we want to calculate two things, or we want to figure out two things. First, we want the acceleration vector. And second, we want to figure out if it's speeding up or slowing down. Notice that with the problem we did before with the cart rolling along the surface, we didn't have any way to figure out whether it was speeding up or slowing down. And that's because the problem didn't give us the direction the object's moving at that instant. You know, something's speeding up if the velocity and acceleration are in the same direction, and it's slowing down if they're in opposite directions. Well, if you don't know the direction of the velocity, you can't figure that out. What that means is in all the other problems, the acceleration was going to be the same no matter what the object was doing, whether it was rolling down at that instant, rolling up at that instant, at rest at that instant. That's not true anymore, okay? So with friction problems, you can't do the problem unless you know the direction it's sliding, and therefore you can always figure out whether the object's speeding up or slowing down. So I'm going to ask that on a lot of these problems. Okay, well, we're going to start it the same way. I'm going to use a rotated coordinate system with the y-axis out of the surface, the x-axis along the surface. And now I'll draw a free body diagram of the block. There's a weight force acting straight down. Oh, I didn't give the mass. Oh, yeah, I did, 2 kilograms. So the weight force is going to be 19.62 straight down. There's going to be a pushing force, a normal force from the surface, like that. And now the friction force is going to be opposite the velocity, opposite the direction of motion. So since this is sliding up the ramp, the friction force is going to be down the ramp, parallel to the surface. And that is going to have a magnitude that's equal to the coefficient of friction, which I gave as 0.1, times that normal force that's pushing those surfaces together. So now we'll go to Newton's second law. Okay, the friction force is in the negative x direction compared to the direction of the positive x there. And so this vector is 0.1 n and then 0 for y. The normal force is what it always is, 0, positive n. The weight force, if I draw this coordinate system, and then I draw the weight force, you can see that this angle theta falls short of getting to 270 when you're going counterclockwise. So it's going to be, so the angle is going to be 270 minus 25 for this problem. For the rolling problem that I did right before, it was 270 plus 25. So this is going to be 19.62 times the cosine of 245, 19.62 times the sine of 245. That's all the forces, and so that's equal to the mass times the acceleration, which I'll just write as a0. And now, like I said, the approach that we're going to use is we're going to use the y equation first to solve for n, and then we're going to plug that n value into the x equation. So the y equation says n minus 17.78. That's the 19.62 times sine of 245 is equal to 2 times 0, so 0. And that tells us that this normal force is equal to 17.78. Now we'll plug that into the x equation. So the x equation says negative 0.1 times this n value that we know now, 17.78, plus 19.62 times cosine of 245. That gives minus 8.29 is equal to 2a. And if you solve this, notice the only variable left is a. So you can solve for a. You get a is equal to negative 5.03 meters per second squared. Well, we want the acceleration vector, so take this variable value and plug it into our acceleration vector like we represented it in Newton's second law. And it gives us that the acceleration vector is negative 5.030. So that's in the negative x direction. And that means that you can also think of it as a acceleration vector with a magnitude of 5.03 in the negative x direction, which is down the ramp. Okay, so that's the acceleration vector. What do we know about whether it's speeding up or slowing down? Well, now we have to compare the direction of our acceleration to the direction of our velocity. Our acceleration is down the ramp. Our velocity is up the ramp. You know, you can think of that as the velocity is this way. The acceleration is this way. And so this object is slowing down at this instant.